So last time we wanted to estimate the number of irreducible polynomials over Fp of degree L, and this estimate is like prime number theorem. So it says that the number of L degree irreducibles in the space of p raised to L polynomials of that much degree is roughly 1 over L in density. Okay, and the error term is also very precise, it is square root of that roughly. So we will show this by invoking this identity. Let's call this this is the recurrence, let's call it R. So we will use the recurrence R to prove this. It's a proof in few lines. So from R what you get is L times pi L is K divides L and K less than L. So K less than L in this case will mean can K be L minus 1? It has to divide L, right? So it's L by 2 or less. So it only goes up to L by 2. That is the reason actually why you will get P raised to L by 2. So this is the error term, and this is significantly smaller than P raised to L. That is what you will see. So this is in particular implying that, so first thing you observe is that K pi K is less than P raised to K. Just from the above expression, because L pi L is smaller than P raised to L, and this is true for all L. So we can observe that K times pi K is always smaller than P raised to K. And then you use this inequality in the sum, for the sum, upper bound the sum, right? So you will get that L pi L is then greater than equal to P raised to L minus P raised to K. Which is greater than equal to P raised to L minus so we can overestimate the sum for all K from 1 to L by 2, and that will give you the result. So this you can now simply estimate by geometric sum, geometric series. So P raised to L right, it is at least this. So that is roughly P raised to L by 2, slightly more than that. So that's the error term. So this means that L pi L is equal to P raised to L plus big O of P raised to L by 2. Right. So main term is P raised to L and the error term is square root of that. So that is the second statement in the theorem. From this you can now deduce inequalities as well. So you can observe at the inequality level here that L pi L is at least p raised to L minus p raised to L by 2. Basically in equation 1, this expression p raised to L by 2 times p over p minus 1, that you can see is at least is at most, it is at most p raised to L by 2 for every L, right. So that minus thing is then greater than or equal to minus of p raised to L by 2. So that gives you p raised to L by 2 as the lower bound. Okay, so L pi L is at most p raised to L and it is at least half of that. Any questions? Fine. So this is true for all p at least 2 and L at least 1, that you can check. It's always true. So what this tells you is we wanted to construct finite fields. Finite field of size p raised to L, now you will construct it by just picking a random L degree polynomial and you will check irreducibility very efficiently. So if it is irreducible, then you have the finite field construction, and the probability that it is when you randomly pick a polynomial, it's reducible or it is irreducible, the probability is at least 1 over L, right. So is that a good probability?
1 over 2L.
Or 1 over 2L. So is that a good probability?
Yes.
Why?
You can repeat the experiment.
Yeah, so if L was say 1000, you wanted 1000 degree polynomial. So this probability seems to be 1 over 2000, which is quite small probability, but you can amplify it by repeating. So you can, for example, pick 4000 random polynomials and calculate the probability that at least one of those is irreducible. So in other words, the probability that all of them are reducible becomes very small. Okay, so you can actually make it arbitrarily close to 1, getting an irreducible polynomial at the cost of more experiments. But that is fine. So this is a fast algorithm. So in practice, this is what is used. Thus, we pick a random degree B polynomial and it is irreducible with probability at least 1 over 2b, and if you repeat it 2b times, say just 2b times, then this probability is at least, so the chance that each of the 2b choices are bad, that is 1 minus 1 over 2b raised to 2b and then complement of that, and that you can check is more than half. Okay, so here is an algorithm that is polynomial time, and it will give you an irreducible with probability at least 50%. You can also increase it by just taking, instead of 2b times, you can take it 10b times. Just simply a constant multiple will give you very large success probability. So any questions? This solves the first problem of finite field construction for codes. So you can now construct finite fields on demand. Second problem was the question of factoring bivariate polynomials. Right. So for that we have currently no algorithm. I mean, we have not seen any algorithm in this class. Only one we saw was for univariate. So now we will reduce bivariate to univariate factorization. We will actually give a general reduction. So this will be over any field. So over any field f, we will reduce bivariate factoring to univariate factoring. And then if you have a univariate factoring algorithm, you can just plug and play. Right. So over finite fields, you have one. Over other fields, for example, over integers or rationals, we still have to find some algorithm. So that will be our long-term goal in the course. This will also raise the question, what about trivariate polynomials and n-variate polynomials? So this reduction will actually generalize to some extent, but to really go to n-variate, we have to use a different method. Okay, that will be another topic to study in this course. So a lot of time will be invested actually now spent in these problems in the course. Half of the remaining time will be spent on these questions. Each of these questions have widespread applications in different areas of computer science. The result, let us look at an example first. So suppose you are given a polynomial bivariate x plus 1 plus y square. Well, this happens to be irreducible, but how do you know? Right? How do you show that this is irreducible? So because for bivariates, you don't even know how to test irreducibility. Right? So this polynomial, intuitively you can immediately see that this is irreducible, but what if it is not? So you want to factorize this. Right? So what is the method that you can try? So in particular, to reduce this to univariate factoring. Basically, you want to eliminate one variable. So what you can do is you can fix that variable. Right? So in this case, you can fix y to be 0, and then you see factorization, x times x plus 1. But that is really no good, because that doesn't really tell you for sure whether f is the factors x and x plus 1 of f mod y, do they really correspond to factors of f without any mod, right? Absolute factors. But anyways, what we can do is we can look at it mod y, then we can look at it mod y square, which is actually the same, again x plus 1. But then you can go to mod y to the 4. Right, and then it becomes slightly different, because x is not a factor anymore, mod y to the 4. And then you go to mod y to the 8 and so on. So how does it work? So first you get x times x plus 1 mod y ideal, then the same thing mod y square, and mod y4, what do you get? So intuitively, the x mod y square should lift mod y to the 4, right, which means that you have to perturb x by some multiple of y square, and similarly x plus 1 you have to perturb by a multiple of y square. So what are these perturbations? So this will work. So if you look at this, then in the y square coefficient you are getting x plus 1 minus x, so that is 1, and y to the 4, next is y to the 4, which is 0 mod y to the 4, right. So this is actually equal to f. These are the factors, and believe it or not, this will actually go on ad infinitum. So for any y to the k you will get a factorization. Okay.
So can we explain these steps once again?
There is nothing to explain. You can just multiply and see that it's f.
So for all k means for all odd k also?
Oh, well, you go to the next 2 power. If it is true for next 2 power, everything below is covered, subsumed. So, but yeah, so this dotted thing will be a theorem that we will do next. But what I have written, that you can just check by calculation. So, and this will actually go on. That will be subject of a theorem which is coming next.
This is reducible.
Yeah, so this factorization will continue like this, but as you can easily believe that this f is actually irreducible. Okay, so it's an irreducible polynomial, but when you do this fixing thing or going modulo and ideal, it happens to be reducible. Right, so this connection from bivariate to univariate is not so easy. So we'll actually do it in steps. So we'll prove some of these things, and later we will see how from this information, by doing some more algebraic operations, some more algorithmic steps, how can you deduce what f really is? Is f absolutely reducible or is f absolutely irreducible? Okay, so we'll do it in steps. We'll add the algorithmic parts in steps. So first step will be to just understand this. How is this factorization lifting? Okay, this we call lift. So factors x and x plus 1 lift mod y raised to 2 raised to k for all k. That we will see next. Although f is irreducible in any field, right, you don't expect f to factor over any field, actually finite field or q. Okay, fine. Yeah, let us understand this this step. So what we are doing here is we factored f, general f, as g0 times h0 mod y. So which is in other words, you factored f x comma 0, that's a univariate, so you factored that by some means, and then you want to lift this factorization. Mod y square, y4, y8 and so on. So under what conditions is this possible? Okay, so this is a lower order problem. Instead of looking at f absolutely, we only want its factors mod y to the 2 raised to k. Right? We just want to check whether it is factorizing for all of these. This is a lower order problem. So first we will solve this. We'll give a formula. Some of you actually already know this trick because you used it in the mid-sem. I saw. Okay, this is called Hensel lifting. So that is the algebraic tool here. So this is what in this course we'll call it Hensel lifting. It's a very old technique which was designed to start a new sub-area in algebra called p-adic analysis. But it's also important in the case of polynomials, which is what you used in the mid-sem, basically for division of polynomials. So this technique is used both in numbers and in the polynomial ring. So we'll do it in the polynomial ring. So let R be a, in fact, for now it's a general ring. Let R be a commutative ring. And I be an ideal. So let F, G, H be in the ring. So if you don't want it too abstract, you can think of R as the polynomial ring. Okay, just like we had before in this example. R is the bivariate polynomial ring, and there are 3 polynomials f, g, h, and g, h are the factors. So such that f is congruent to g times h modulo this ideal. Again, this ideal you can think of as the ideal y, or its square, and so on. So when you are at a at an intermediate step f equal to gh mod I, lifting means that you want to lift g to mod I square, the factorization mod I square, right? So when is that possible? It is not always possible. We'll see an example later. So we'll need more conditions here. One condition is that G and H should be somehow co-prime, which will not make sense for every ring. But what will make sense is Bezout identity. So we'll actually assume Bezout identity. So we'll assume that AG plus BH is 1 mod I. So this is what is called pseudo coprimality. So you want GH to be somehow coprime, and these are the factors mod I. So these are pseudo coprime factors mod I. Okay, this is what you start with, and then you want to go to the next step. You want to lift this picture mod I square, which means you want G prime, H prime, A prime, B prime. You want 4 things to be lifted. So yeah, so formally there is a lot of equations. So let us write that. So it says that we can compute, which is very efficiently, can efficiently compute G prime, H prime, A prime, B prime in R such that, so G prime should be, in fact let's use tuple notation. So G prime H prime would be the same as respectively G and H mod I. Okay, this is a condition which is important for lifting, that G and G prime should look the same mod I, but different mod I square possibly. And F is G prime H prime mod I square. What is I square? I think we defined it in the first class. This is just pick any two elements in I and multiply them. So you have these products and then you generate the ideal by them. That is called I square. It is simplest to understand in the case of principal ideal, like when you had y, ideal y, then squaring is just squaring the single generator. But this theorem of Hensel lifting is very general, so it will work for any ideal. Okay, principal ideal will have no utility here. And second is that they are pseudo coprime. And as if this was not enough, the last property is that G prime H prime are unique up to unit multiplication. Right? So factorization, even the polynomial ring, it is unique only up to unit multiplication. You can always multiply by 2 and divide by 2 in the factors, right? So those things you can do here also, but up to those unit multiplication, G prime H prime are unique. So G prime in particular is unique. That's the last. And G prime H prime are unique up to units. So this is a big statement. Any questions about the statement? Proof will be equally long. Sorry?
Degree of A and B.
Yeah, so you are jumping ahead. What is the meaning of degree in a ring R? It has no meaning. We are first proving a general statement. Hensel lifting in the most general form is this. Yeah, so if the statement is clear, then let us move to the proof of this. Yeah, any ideas? How will you get G prime? You have G, H, A, B. From these four things, you want to get G prime. What is the formula?
G plus I into something, so that what will be the result?
Yes, so G prime has to be G mod I, so which means that you want to perturb G by an element in I. Right, so that element you want to find. But obviously it has to be a very special element. At this point it is not even clear why that will exist, because it has to satisfy all these conditions, congruences, mod I square, which is the next precision. So in terms of precision, actually we are increasing the precision, right, because I square is a smaller ideal. So when you go modulo a smaller ideal, you have to do more, you will get a more precise answer. So most precise answer you will get mod 0. Right, that is your limiting case. So you have to increase precision. That's a non-trivial thing. So what actually we will use is what is already given, which is f minus gh. F minus gh is an element in the ideal. We'll try to use that in the perturbation. So consider m to be f minus gh, which is an element in the ideal. And for that you define g prime h prime as follows: g plus bm and h plus am. Okay, a and b were given to you. M is also kind of given to you because gh were given. So if you look at this, this actually works. So obviously you will find this in by doing some calculations which I am skipping. I am just directly giving you the answer. Okay, but these are easy to find. So once you have this, you can just check that f minus g prime h prime is which is, so f minus gh is m, and then you have in the product you are getting coefficient of m bh plus ag. And then you are getting m square, but m square we will actually call it 0 by going mod I square. Right? And what is 1 minus ag minus bh? That is again an element in I. M is also in I. So this is actually 0 in I square. So that is it. That's the check. Right? So the algorithm is then very simple. Given a, b, f, g, g, h, you have designed g prime h prime. It's a completely closed form expression. Next thing to show is why are these g prime h prime pseudo coprime. So we have to give a prime b prime. Yeah, so that again you can reverse engineer. I'll just give you the expression. So that will be, now you consider m prime to be 1 minus ag prime plus bh prime. So this m prime is also in I. Do you see this? This is 0 mod I. Why is that? Yes, because g prime and h prime are g comma h, and then then ag plus bh is 1 mod I. So this actually remains in I. We'll use this to perturb a and b. So define a prime b prime as follows. And then just check what you are getting when you calculate a prime, g prime, b prime, h prime. So this is ag prime plus bh prime times 1 plus m prime. So we are doing this now mod I square, right? That's the modulus. What is ag prime plus bh prime? That is 1 plus m prime by definition, 1 minus m prime. which is 1 mod I square. Is that clear? This product is 1 minus m prime square. M prime square is in I square. So this is 1. So which shows that G prime H prime that we have constructed, they are also pseudo coprime. And you get the Bizu identity explicitly. Okay. Any questions? Why are these? Why is this construction unique? So I just gave you one construction, right? Why is there no other construction possible of G prime? So that you have to separately prove. So suppose it is possible. Suppose there are some other lifts of G and H respectively. Then what do you have? F is GH and also G prime prime H prime prime mod I square. Sorry, I. This is prime. So mod I square, you have two factorizations, G prime H prime as before, as defined or constructed, and G prime prime H prime prime which somebody else gives you. So let us look at the difference of G prime and G prime prime. Okay, let us look at that. So let me just put it here directly. So this is G prime plus M1 and this is H prime plus M2. M1 is G prime prime minus G prime and so is M2, analogous to this H prime prime minus H prime. So where does that put M1 in?
I.
Yeah, you cannot say I square, you can only say I. So you know that both G prime prime and G prime, they are same mod I. So the difference is actually 0 mod I, right? So M1 and M2 are in I. Okay. So what do we do next? Yeah, I think we just multiply and take the difference. Just so basically G prime H prime is equal to this product. So you minus G prime H prime from this side and that result is 0. Let's write down that congruence. So that congruence is M2 G prime plus M1 H prime is 0 mod I square. Because M1 M2 is 0 mod I square and G prime H prime has been cancelled. So you actually get a relationship between M1 M2. Right? These M1 M2 given to you by somebody else are actually related this way. What do you do next? Yeah, use the Bizu identity for G prime H prime. Yeah, you might want to cancel these things out, but that is actually not legal, may not be legal in this arithmetic. So the only thing you can do is multiply or add. It's a ring, right? So let us just multiply G prime by A prime. And then kind of cancellation effect will happen. So what you will get is, so we had M2 G prime A prime plus M1 H prime A prime is 0 mod I square. And what is A prime G prime? So, okay, where does that take us? So, we are getting M2 H prime will take out M2 B prime minus M1 A prime mod I square. Okay. Remember M2 was, how did we define?
H prime prime minus H prime.
Right. So, this means that H prime prime is now H prime 1 plus this thing. So, that is it. We have now actually a relationship between H prime prime and H prime. Right, H prime is what we had, what our algorithm had constructed. H prime prime is something totally arbitrary given to us, arbitrary solution given to us. It is actually just a multiple of H prime. What can you say about this multiplying factor 1 plus M2 B prime minus M1 A prime? What did you say about M2 M1? They were in I, right? So, this difference is also in I, because I is an ideal. So, what can you say about 1 plus I? This is actually a unit. What is the inverse of this? Yeah, so mod I square, it is a unit, because if it was 1 plus small I, then you multiply it by 1 minus small I, and that gives you 1. So, this is actually an invertible element. So, that is it. So, this is this whole thing is a unit. So, the reason is just that 1 plus I, 1 minus I is 0 mod I square. Sorry, 1. Because I square is 0 mod big I square. Okay, so as promised, H prime prime and then analogously G prime prime, they are actually just unit multiplication by a unit of what we had constructed. Right, so we have proved everything that was claimed. G prime, H prime have a very simple form. They are co-prime, and there is no other solution. So that completely solves this problem of lifting. Well, okay, there was one thing, that is this assumption needed, the assumption of co-primality. This extra condition that we needed, AG plus BH equal to 1 mod I. What if GH is a non co-prime factorization? Will it lift mod I square? That is the only issue left. So actually that condition is required, otherwise lift may not exist. Let's see that. Is crucial for lift. So let's see an example for that. So the bivariate example with the ideal y. So let's take f to be x square plus y. So mod y, the factorization of this is x times x, which is non coprime. Will that lift? So suppose it lifts, right? What do you get? Say it lifts like this: x plus multiple of y. So some a perturbation, and here some other perturbation, mod y square. So which will mean what? So you take the difference of these two, sorry, not these two, you take the difference of actual f. So x square plus y minus this mod y square is what? So x square will cancel and this y square will also disappear. So what will you get is, what you get is 1 from here and ax plus bx. Right? Is 0. So y square divides this, meaning that y has to divide this other factor. Right? You deduce this. This is if and only if. This is also if and only if. And so can this happen? Can there be bivariate polynomials a and b such that this thing happens? So what is this thing? So this is a at x comma 0 and this is b at x comma 0 times x should be equal to 1. Right? This is a equality in the univariate polynomial ring, which cannot happen, right? Because this in particular means either x divides 1 or left hand side is 0. Actually, either way x has to divide 1, which is a contradiction, right? So this cannot happen. So this means that actually there is no lift mod y square of that factorization, right? So you have to assume coprime factorization, so which actually gives you a complete understanding by Hensel lifting theorem, gives you a complete understanding of how lifts happen. So factorization has to be coprime, and when it is coprime, then it can be lifted to coprime in a unique way and in a very simple way. Okay. Yeah, last thing that remains is what Ashish was worried about, that what happens to degrees when we are talking about bivariate example. So the special case of this Hensel lifting theorem, when R is bivariate, and say you started with a nice factorization of f into g and h, where both g and h are monic. So g is of degree d prime and h is of degree d minus d prime in terms of x, and degree of f is, say, in terms of x it is d. So you start with a nice monic coprime factorization. What is the degree of g prime with respect to x? Does it remain the same as before d prime? Can it decrease, increase? So those questions. So basically, we want nice factorizations to lift to nice factorizations also in the bivariate case. I mean, in the bivariate case, we want more properties than what we are promising here, because here we did not talk about degree. So that actually is again a long calculation in itself, the special case. So let us do that next. So a corollary of Hensel lifting So this is for the bivariate case. Because this is actually the case in which we were originally interested in. So we'll have some factorization mod y to the k, and then from there we'll want to go to mod y to the 2k. That is the motivating case, right? So this will now give the extra calculations here. So say f g times h mod y to the k, and this is co-prime, so there is ag plus bh moreover g is monic. Actually I don't need everything monic, just g is given to be monic. So that is the kind of the key, which was key new thing we want to study, that what happens to a monic factor, right? Monic again, remember, is g is bivariate in x and y, and look at the highest monomial in x, the coefficient of that is 1, right? That is what monic means. So suppose this is so this is actually interesting when g is giving you a root of f, right? So x minus a of y, for example. When g is of this type, x minus a of y, so a of y is actually a root of f with respect to y. So what we want to study is when g is of this type, what happens to it when you lift it? Does it retain that form? That is the motivating case. So obviously the conclusion, the claim is that we will be able to achieve that form. So then we can lift it to g prime, h prime, a prime, p prime mod y raised to 2k such that g prime is monic with respect to x and it is unique. Yeah, this will need more care than what we did before, because we have to make sure that garbage monomials in x are not added in g, right? Because we want to make a statement about the highest degree x monomial. So nothing greater than that should be added in g when you are trying to lift. So actually the proof, the correction will not be that difficult. So what you do is compute the lift by previous Hensel lemma, previous algorithm. So just use the previous the theorem algorithm in the theorem. That will give you big G and big H in higher precision, y to the 2k. You started with the low precision small g times small h mod y raised to k and lift that to this. Now the problem is that this big G may not be monic anymore because certain things were added in G where higher degree x monomials most probably have been added. We were not careful about that in the proof. So in the bad case, G is not monic. Then we change it. So let us correct it to G prime. To G prime, which is it will basically be, sorry, yeah, it's not immediately visible here. So we'll perturb G by R y to the k, where R is given by big G in a very specific way. So R is by the division algorithm. So use division algorithm with the G as small g as divisor. Why? So why is that possible? So this big G minus small g, that by Hensel lift is divisible by y raised to k. So you can divide that, you can get a polynomial, and that bivariate polynomial you want to run division algorithm where the divisor is small g. But remember that these are bivariate polynomials. So how do you do division? Sometimes you cannot run division algorithm in bivariate. The only problem is that small g may not be monic. So small g, its leading monomial in x may have some polynomial sitting in y, and then you cannot run the division algorithm. But here that problem is not there because small g is monic. So small g is something like x square plus y, and you can run the division algorithm with respect to x. Right, so you do that, that is a fast algorithm, and you will get Q and R. So that is the output you get from the division algorithm. Okay, so R is something whose degree is less than the degree of G with respect to x, right? And you discard Q, you use R to define G prime. That's all. Okay, that is the modification. Yeah, why this works is just a simple calculation now. The algorithmic steps are only this. So just observe that G prime is monic. With respect to x. Why is that? Well, because by this division algorithm, R has a lower degree in x, and we are perturbing G only by lower degree, multiplying by y raised to k, but that won't affect the monic assumption on G. So the new polynomial G prime is also monic. Okay, that is the trick. And why is this G prime a factor of F? So that is a simple calculation. It's a factor only mod y to the 2k. Okay, it's a factor of F mod y raised to 2k. So why is that?
H will change.
Yeah, that is fine. H will change, but why is G prime a factor?
When you are making G prime a factor, H will change accordingly.
No. You cannot make a non-factor a factor. G prime already has to be a factor. So why is it a factor? Independent of H. So let's do that calculation. So G prime is G plus R y raised to k, and just from the previous slide, R y raised to k is this. Which is big G minus q small g y raised to k. Yeah, then you use the special modulus you have. You go mod y to the 2k. So, and when you go mod y to the 2k, this small g you can replace by big G, because they are the same mod y to the k. Which is G times 1 minus q y to the k. Fine. So actually in this special modulus y to the 2k, G prime is nothing but just a unit multiple of big G. So obviously it's a factor of F. Right, that's all. So yeah, now you can just suitably pick H prime. So H prime you can pick H times the opposite sign. So 1 plus q y raised to k, and then you will see that F congruent to G prime H prime mod, which is also the same as G times H, mod y to the 2k. Okay. So you basically mod y to the 2k, you have two lifts, one that Hensel gives you, that is big G big H. But if big G happens to be non-monic, then you just do some basically do one division algorithm and modify it. The division algorithm is basically then giving you a q which you are using to multiply big G with. Okay, you are basically doing that perturbation by multiplication, and then in the end you get G prime to be monic. Okay, last thing was why is G prime unique? And here unique means without any restrictions, without any transformations. It's absolutely unique. It's absolutely unique because suppose you have G prime prime. So this G prime is monic factor of F, and G prime prime is also both lifts of G. By Hensel lemma, there should be a scaling factor which is a unit, but that is not possible because monic means that the leading coefficients are both 1. So 1 divided by 1 is just 1. So they have to be identical. Okay. So that uniqueness, it actually immediately follows from Hensel. So G prime is unique, and that is without restriction. So absolutely. um, by Hensel lemma, by Hensel lifting. Okay. And the fact that it is monic. Okay. Yeah, so that is the major engine of all future factoring algorithms. Okay, this the first theorem is the major engine, and this special case is specialized for bivariate. But the first theorem itself has actually many interesting special cases. This is for bivariate. You can talk about number theoretic analogs. So, for example, you have a factorization of a univariate modulo some prime p. Then you can ask the question: will it lift to mod p square and mod p cube and so on? Both these special cases we'll be using. The bivariate we'll use immediately in the next class. The number theoretic one we will use when we try to factor integral polynomials. Okay, so in all the future applications or studies we will be using this. And then finally also in the n-variate factorization we'll use this in a more complicated way. Okay, so this actually these calculations form the engine of much of what we'll do before the end sem. Any questions? Okay, so thanks. Stop.